If you cannot find the seats here, there are seats in the balcony. But this was expected to be a full sold out crowd here today. No question about that. First of all, I just want to make sure that everybody knows that this is the special event of the Young Scientist Roundtable. Those who think that they are here in error, this is the time to go out of the auditorium. My name is Vinod Padde, and it is my privilege to welcome you all on behalf of the Young Scientist Roundtable team, which puts this program together. Most of you know that this is an annual program. We have event once a month throughout the school year. Today is a special event. We have Dr. Squyres from Cornell University, and this is what we call Celebration of Science. Dr. Squyres is the James A. Weeks Professor of Physical Sciences at Cornell University in Ithaca, New York. He received his BA in Geological Sciences from Cornell University in 1978 and PhD in Astronomy in 1981. He worked as a postdoctoral scientist and researcher at NASA Ames Center on the West Coast prior to returning to Cornell as a faculty member. His research area has been planetary sciences with a focus on large solid bodies in the solar system. This is the second time that Dr. Squyres is here. I don't know how I was able to get him in 2010, but after the program in 2010, he was impressed with one young girl, barely 5 years of age, with pink dress. This young girl, after this session, approached him and asked him one of the most brilliant questions. How come the robots know where they are? What kind of magnetic system is there? North, south pole, things like that. So after that particular session, Dr. Squyres told me, Cornell doesn't pay me necessarily to run this rovers program or teach, but Cornell pays me to meet with the young girls with pink dress. So that's what the thing that I was able to use, and tell him that I will get you few more young girls with pink dresses this time. Will you please come to the Young Scientist Roundtable? And that's the way in which I was able to bring him here. Dr. Squyres is best known for his pioneering work in the robotic explorations of Mars. As the principal investigator of the Mars Exploration Rovers mission, MER, he assembled a team in 1987. Rovers landed on Mars in 2004, and since then, he has been the face and voice of the mission. In 2005, he published a book, Roving Mars, Spirit, Opportunity, and the Exploration of the Red Planet. And the same is the title for his talk today, Roving Mars, Spirit, Opportunity, and the Exploration of the Red Planet. Let's welcome Dr. Squyres.
All right. Let's see. Yeah, that's great. Bring the house lights down so people can see. So, if I'm doing my math right, today is day 4,897 of our 90-day mission to Mars. We're still going, and what I'm going to try to do in the next 45 minutes or so is just share with you the adventure story of the Mars Exploration Rover project and some of our discoveries. So this is Mars, the object of our affections. It's a terrible place. If you went there, you would hate it. The average temperature is 60 degrees below 0 Celsius, colder than Minnesota in the winter. It goes down to minus 100 at night. If you took all the water vapor in the Martian atmosphere and you condensed it out on the planet's surface, you would make a layer of froth that's barely 1/100 of a millimeter thick. So Mars is a cold and dry and desolate world today. But in the past, it was different. This is a picture taken from orbit of a valley snaking across the surface of Mars. It's only a couple 100 meters wide, and if you look at the upper right, you can actually see the tiny channel through which the water that carved that valley flowed. You can't do this on Mars today. On Mars today, it is too cold to allow something like that to happen. So features like this are a clue that in the past, Mars was different. It was warmer, it was wetter, and it was possibly more like Earth. Now, any geologist will tell you that if there's erosion, somewhere else there has to be deposition. And there are places on Mars like this where you can find these beautiful sequences of layered sedimentary rocks. Now, the great thing about layered sedimentary rocks is that they preserve in their details, their texture, their chemistry, fundamental information about the conditions that existed when they were laid down. And so if you can build a piece of hardware, if you can build a robot with the right capabilities, and you can go and read the story written in those rocks, you can learn whether or not Mars might once have been a world capable of supporting life. This picture was taken at Cape Canaveral in Florida about 14 years ago. You can see the rover Spirit in the foreground, all tricked out, ready to go to Mars. Rover Opportunity is in the background against the back wall there. It doesn't have the wheels on yet. I'm the good-looking guy in the white suit. These rovers are our surrogates. We experience Mars through their sensors. Now, it shows what the vehicle looks like, 6 wheels for driving around, great big solar arrays. The scientific instrumentation that we use to investigate Mars comes in 2 parts. One is supported by that big flat white stovepipe-looking mast. Okay, there's a set of cameras at the top, color stereo, high resolution. They're the cameras that take those beautiful pictures you can download on the web. There's also an infrared spectrometer. The infrared spectrometer lives down inside the rover, and it looks up that big fat white pipe. It's hollow on the inside, and there's mirrors at the top. It's a periscope. And so it gets this infrared spectrometer gets the same view of the countryside that the cameras do. On the front end of the vehicle, there's an arm. The arm has a shoulder, an elbow, and a wrist. It has exactly the same dimensions as my arm. That is purely a coincidence. And on the end of the arm, there are 4 devices. There's a microscope, 2 more spectrometers to tell us in detail what the rocks are made of. And then we got this wonderful device that we call the RAT, R-A-T, the rock abrasion tool. And it's a diamond-tip grinding tool that can grind away the outer surface of a rock so that we can see inside the rock with the other instruments. Now, the spacecraft that we designed to get the rovers to Mars is built like one of those Russian doll sets, you know, where there's a doll inside a doll inside a doll, right? Okay? So the rover, which you can see at upper right here, folds up in this horrifyingly intricate fashion. So it makes this compact little package that then fits inside the lander. The lander's shown at lowered right. The lander has those 3 things on the corner shown in bright colors there. We call those petals because they're like the petals of a flower. And what they do is they fold up around the rover, enclosing it, encasing it, protecting it for the ride to Mars. So that folded up package is then enclosed in turn in another shell. The red thing at the bottom, that's called the heat shield. That protects the vehicle as it plummets at high velocity through the Martian atmosphere. There's a cone-shaped thing on the back we call the back shell. And then that blue kind of frisbee-looking deal on the back end of it, that's what we call the cruise stage. And the cruise stage provides electrical power, propulsion, the stuff we need to get us to Mars. Here's what it looks like when it's all put together. Some assembly required. This is at the Jet Propulsion Laboratory in Pasadena, California, where we built the vehicles. We launched in the summer of 2003 from Cape Canaveral in Florida, 2 beautiful launches, one in the daytime, one at night. It took the spacecraft about 7 months to get to Mars. When you get to Mars, you hit the top of the Martian atmosphere going Mach 27, 27 times the speed of sound. The heat shield bleeds off that kinetic energy as we fall through the Martian atmosphere. And once we've slowed down to a nice leisurely Mach 2, we throw out a supersonic parachute. We learn the hard way that supersonic parachutes are very difficult things to design and build. The lander descends on a long cord, and what you see at lower right, this is what it looks like as it's still screaming down towards the Martian surface at about 200 kilometers an hour. You don't drift down lazily on a parachute on Mars. The Martian atmosphere is very, very thin. We had a terrible time with our parachutes. These are pictures from the first test of the parachute design that we thought was going to land us on Mars. We did these tests at a National Guard gunnery range outside of Boise, Idaho. It's the kind of place where you can drop big, heavy things from the sky and they won't kill anybody. We took our test article up to about 4,000 feet with a big helicopter. We dropped it, we deployed the parachute, it blossomed, and it made this perfect orange and white bowl, and then it just exploded. It just ripped to ribbons, and parachute after parachute failed. What had happened was, as our understanding of how big the rover had to be to do its job matured, our estimate of its size and its weight grew. The thing got heavier. And by the time we did these tests, the rover was too big and too heavy for the parachute to land it. So we had a very serious problem. We embarked on a crash program of parachute redesign, trying to design 3 different parachutes in parallel, praying that one of them would work. One of them did work. This is from a test in a big NASA wind tunnel out on the West Coast. This is the first successful test of the parachute design that actually landed us on Mars. We had our first successful parachute test just 8 months before we had to be on top of the rockets in Florida. It was terrifying. We land using airbags. What? That's an airbag engineer being consumed by his work. We land using airbags. They're just like the airbags in your car, except a lot more expensive. And they inflate explosively around the vehicle about 10 seconds before touchdown. We fire some rocket motors, and we let the airbags fall to the surface, and they bounce. And they bounce, and they bounce, and they bounce, and they roll, and they roll, and they roll. And they can bounce and roll as much as a kilometer before they finally come to rest. We had a terrible time with the airbags, too. We did our airbag tests in the world's largest vacuum chamber in Sandusky, Ohio. I know some of you young scientists, young engineers, you're going to grow up, you're going to become an engineer. I'll just warn you, you're going to have days like this. Look at their faces. Okay? We tested the airbags and they just burst. They popped. Too much stress on them. Again, it was too heavy. The only way to solve that problem was to add more layers of fabric to the airbags, making them heavier still, and that made the parachute problem even worse. We finally got it to work. The picture on the left is from one of our first successful airbag tests, and then the ultimate test on the right, you can see airbag bounce marks on the surface of Mars. Now, once we land, the lander pedals open up, flips the vehicle upright, and there, tucked inside, looking nothing like a rover yet, is our vehicle. What it now has to do is origami in reverse, unfolding itself in stages to turn itself into a rover. Now, there were many parts of this process that scared me, but this part here, with all the gears and motors and springs and hinges and latches, was terrifying. What you see right there, those are the solar arrays. Those are the life-giving solar cells that must deploy the first day on Mars, or we don't survive the first night on Mars. The camera mast comes up, the antenna goes out, and once we get to this configuration, we're safe. The sun is shining, so we have power. The camera is up, so we can take pictures. The antenna is out, so we can transmit those pictures to Earth. All of that happened pre-programmed in the first 2 hours after we landed. But once we get to this configuration, we can't go anywhere because the wheels are still folded up underneath the vehicle. There's another step, and it's even worse. Watch this. There's a jack, like the jack in your car, and it lifts the vehicle up. And now watch what the front wheels do. Watch this. It's been 14 years. I still get the heebie-jeebies when I watch that. Okay, if those latches don't latch, you're done. Fortunately, they worked. Now, when we designed this whole cockamamie system with the Mach 27 and the parachute and the airbags and the bouncing and the unfolding and all of that, we thought that once we got to this stage, with the rover standing up on the lander, we were kind of home free. Just cut the cable that connects the rover to the lander, and we just go monster trucking down onto the Martian surface, and it's all going to be good. Then we did some tests. Yeah, this is a bad day. It turns out that when you drive one of these vehicles off a lander, it can flip itself upside down. So we had to figure out a solution for that one. You actually saw the solution in the little video clip that I showed you. We made some ramps out of fabric. And the fabric stows between the pedals. And when the pedals open out into place, the fabric snaps into place, and it makes a fabric ramp that we can drive down. The fabric is the same stuff that the airbags are made of. It's very tough, and we had lots of it. And then we can go driving down onto the Martian surface. Now, once you get on the Martian surface, you got to deal with the fact that Mars ain't exactly paved. Okay, there are rocks and dunes and drifts and things that you have to go over, and so our mechanical engineers had to design a suspension system that could conform to whatever topography we might encounter. It's a mechanical wonder. Here you go. This is it in action. Watch the wheels. Watch the wheels as it encounters this topography. I mean, if we find a corrugated metal roof on Mars, we're all set. It's going to do a little pirouette here. It's really a remarkable system. Works extremely well. All right, now driving. How do you drive these things? What I wish I had, of course, is a joystick. Right? What I want to do is I want to sit in my office and steer the thing around rocks and obstacles, but you can't do that. On the night when we landed, when Mars and Earth were pretty close together as these things go, it took 10 minutes for a radio signal traveling at the speed of light to get from Earth to Mars. Something happens on Mars, 10 minutes for the result to come back. That's a 20-minute round trip time. If I try to joystick it, I'm going to run into a rock. So what we've had to do instead is to endow the vehicles with vision and intelligence and the ability to make their own decisions about what is safe and what is not. Each vehicle carries a pair of these googly-eyed, wide-angle cameras down on the front bumper and the back bumper. They take these kind of fisheye pictures, and often those pictures don't come down to the ground. Instead, what the rover does is it will look at the terrain in front of it and build up like a three-dimensional model in its computer brain of what's in front of it. And it'll look at that model and it'll decide that's safe enough that I can drive over it, or that's dangerous enough that I have to drive around. And we can actually program different levels of courage or cowardice into the vehicles depending on how dangerous we think the terrain is. Here's a drive that the Spirit rover did early in the mission. The first part here we commanded explicitly. We told it where to go. But from here on, from that point on, the Spirit rover is making its own decisions. So right about here, it finds a scary pile of rocks. Doesn't know what to do, thinking about it, says, okay, I'll do it this way. I can do it backwards. Makes that beep, beep, beep sound. You know, this is backing up. Another scary pile of rocks here, thinking about it, doesn't know what to do. Okay, I'm going to go this way, and I think they wanted me to stop right here. All done. They're pretty smart vehicles. Okay, the RAT, the rock abrasion tool. This is one of the most important pieces of hardware on the vehicle. When a rock sits on the surface of a planet for an extended period of time, it undergoes a process that geologists call weathering. Humidity, wind, sunlight, dust, these are all things that can change the outer layers of a rock. They can effectively destroy the evidence. And to get at the evidence, the scientific clues that we want, we need to be able to drill through that outer weathered surface into stuff underneath. So the RAT is a diamond tip grinding tool, and there are these diamond grinding heads that spin at 3,000 RPM, and we use them to drill into solid rock on Mars. Now, the RAT is effectively a power tool. It's the world's first interplanetary power tool, and as with all power tools, you have to be very careful when you use it, because you don't want something like that to happen. I'm sorry, that's such a cheap laugh. I thought the wheel coming off was a nice touch. All right. Let's go to Mars. So the landing site for the rover Spirit is shown here, that big blue crater that you see in the middle of this topographic image. It's called Gusev Crater. It's 160 kilometers in diameter, 16 degrees south latitude on Mars. The reason we chose it is this thing, right here. There's a great big dried up riverbed flowing into that crater. Now there's no water in that river now, there has not been for billions of years, but this is a big hole in the ground with a dry river flowing into it. There has to have been a lake in Gusev Crater at some point in the past. We landed and we saw this. Really smooth, really flat. I managed to convince myself for about 3 days that this is what a Martian dry lake bed should look like. But then we started looking at the rocks. The first rock that we looked at carefully with Spirit was this one. We named it Adirondack. It's about this tall. We hit it with everything we had. We looked at it with all our spectrometers. We drilled a hole in it to it with the rat. We did everything we could to it. That's not a sedimentary rock. There are no layers in that rock. That's a piece of lava. And every rock for miles in every direction is a piece of lava too. Mars faked us out here. I still believe that those layered sediments must be down there somewhere, but what we learned when we landed, and this was a bitter disappointment at first, was that the sediments had been covered with lava and there was no way for us to get to them. That was bad news. Now when we landed, this was with a vehicle that was designed to last for 90 days and to drive 1 kilometer over its lifetime. 2.5 kilometers off to the southeast, there was this beautiful range of hills. We named them the Columbia Hills after the Columbia Space Shuttle, which had gone down during the period of time when we were developing the rover. Each of the summits is named after one of the Columbia astronauts. And when we realized that every rock that we could see in almost every direction was lava, we realized that if we were going to do anything other than look at lava with this rover, we were going to have to sprint rover speed to the Columbia Hills and try to get there before the mission was over. On day 156 of our 90-day mission, we reached the base of the Columbia Hills and everything changed. This is the biggest, tallest of the Columbia Hills. This is Husband Hill. It's named after Rick Husband, who was the commander of the Columbia when it went down. And we climbed it all the way to the summit. As we worked our way up, we began to see layered rocks. As we worked our way up, we began to see minerals that could only form in the presence of water. So now we were beginning to see the kinds of things we had come looking for. We spent almost 500 Martian days climbing to the summit. Sorry, what's going on? Oh dear, okay. Is there a doctor here? Let's get some lights. Let's get the house lights up. House lights up, please. Is there a doctor anywhere here? Okay. Let me have the house lights up, please. There we go. Thank you. All right, everybody, I appreciate your patience. We got priorities here, so let's take care of this, and then we'll get back to business when we can, if we can. really appreciate everybody's patience. Okay, we're going to get back to it here. Could we bring the house lights back down, please? Thank you, everybody, for handling that so well. Really appreciated that. Okay, so we worked our way up to the summit of a mountain as tall as the Statue of Liberty. Again, house lights down, please. Doing the first ever mountaineering on Mars. Like any good mountaineer, when we got to the summit, we took a picture. This is the picture from the summit looking to the south. House lights, thanks. They're working on it. As we speak, the Spirit rover is right there. Spirit lasted for 6 years, again, against a design lifetime of 90 Martian days. And that is where Spirit we finally wore it out. Now, Spirit had a tough time. Spirit had a very, very difficult mission. We really beat on that rover very hard with all the mountain climbing and all of that. And about 800 days in Spirit's mission, the right front wheel failed. It would no longer turn. And what that meant was that we had to then drag that dead wheel backwards through the soil. And a rover that used to go 100 meters a day, now a good day was 10 meters. But there was a silver lining to it, and that was that we dug, as we drove, this marvelous hundreds of meters long trench through the Martian soil. And every so often, something wonderful would pop up in the floor of that trench. We were driving one day through a little valley, and at the end of the drive, the soil in the bottom of the trench came up as white as bright snow. This caught our attention. We got our spectrometers, we made a measurement of the composition. It's not snow at all. It turns out that stuff is 91% pure silica, SiO2. This is not quartz, this is not beach sand, this is opal, like the gemstone. This is the stuff that forms in hot springs and hydrothermal systems, geysers. So what this is telling us, this silica deposit in this little valley on Mars is telling us that at this place, billions of years ago, there was a hot spring on Mars. There was hot water coming out of the ground. This was a habitable world. So this is one of the rover mission's most important discoveries. We, of course, named this valley Silica Valley. Spirit also had a tough time in another way. There's a lot of dust in the Martian atmosphere, and the dust settles out onto the solar arrays. This is a rover selfie. Okay, this picture was taken about 250 days into the mission, and the solar arrays are brown. Now, when the rovers first landed, they were brand new, straight off the showroom floor. Those solar arrays would put out about 900 watt-hours of power per Martian day. That's enough energy to run a 100-watt light bulb for 9 hours. As the dust accumulated, the power went down and down and down and down and down, and by the time this picture was taken, the power was about 250 watt-hours. And death is right around 150. So Spirit was close to the end. And then one wonderful day, this happened. A lucky gust of wind hit the vehicle, and overnight the power went back up to 850 watt-hours. Pure dumb luck. It was as if that had happened. In reality, it was probably something more like this. Check this out. Look at that. Dust devils, little Martian mini tornadoes that we see whirling across the sea. And I'll play this again. I love this video. You can almost see Dorothy and Toto flying through the scene. And probably what happened was one of those hit us and cleaned the vehicle off. Watch this. What was that? Anybody know? No? Eclipse. Good, I heard it. Eclipse. Mars has 2 moons. The moons are named Phobos and Deimos. This is the moon Phobos passing in front of the sun. This is the first solar eclipse ever witnessed from the surface of another planet. There's no science in this at all. We just did it because we could. And that's a sunset. On Mars, because of the very, very fine reddish dust in the atmosphere, the sky is pink in the daytime, and it turns blue at sunset. It's the opposite of Earth. Okay, let's move on to opportunity. We chose the landing site for opportunity not because of the topography. No hole in the ground, no dry riverbed. We chose it because of the chemistry. The picture at the right is data from orbit from an infrared spectrometer. Blue is boring old lava. But the yellow, the green, the red, that's a mineral called hematite. Hematite is an iron oxide. It's a mineral that is present in rust. And it's a mineral that usually forms in the presence of liquid water. So this is like a chemical beacon visible from orbit saying, hey, water was here. Come here. Now at the lower left, you can see what the landing site looks like in pictures. It's very smooth, very flat, safe for landing, easy for driving. The thing that made me nervous about this landing site was I was afraid that it was so smooth and so flat that nowhere would we find the topography we would need to expose bedrock. I need not have worried. These are some of my favorite pictures from the whole mission. As our lander was descending towards the surface, there was a camera on the underside looking down that had enough time to snap off 3 pictures. You can see those 3 pictures at the top. If you look at the right, there's a big impact crater. Just to the left of the impact crater is a little black dot. That black dot is the shadow of the parachute. Okay? What you're seeing at lower right is just the same thing being projected obliquely. The red curve is the reconstructed trajectory that our vehicle used as it was going through the landing process. So we're coming screaming in from space, 200 kilometers an hour. We fire the rocket motors, we drop the airbags to the surface, they start to bounce. The wind that day was blowing from the south. And so the trajectory bends to the north, bounce, 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 and then reading the green perfectly, it bends to the left and goes right into a little 20-meter diameter impact crater. Tiger Woods on the best day he ever had could not have pulled this off again. It was just pure dumb luck. We opened our eyes and there was this spectacular outcrop of layered bedrock right in front of the rover. Now we realized very quickly that we were in a crater, but we didn't know what crater we were in. So we didn't know how big the crater was, so we didn't know how far away the crater wall was, so we didn't know how big the outcrop was. And on the night that we landed, the name that my team gave to this massive outcrop that we were going to have to somehow figure out how to negotiate, they called it the Great Wall. Then we took some stereo pictures, and we did a little trigonometry. Little tiny outcrop, great big rover, the Great Wall was about that tall. But it turns out that that was part of its charm, because what it meant was that the layering in the rock was very, very fine. Now, the thing that brought us here was hematite. So we went looking for the hematite. We found it right away. This is a map that we made with our infrared spectrometer. Red is a lot of hematite, blue is none. There's plenty of hematite on the floor of the crater and outside the crater. There's some in the outcrop, but not a lot. And then down on the crater floor, there are these splotches in blue that have no hematite at all. The splotches are airbag bounce marks. So when you bounce in the dirt at this place on Mars, hematite goes away. It was the first of many mysteries. I showed you this picture before. You can see the very smooth bounce marks, no hematite in them. In between where all the gravel is, that's where the hematite is. So we're thinking, aha, the hematite must be in the gravel. We drove off the lander and looked down at the gravel, and we started to notice that these grains of gravel looked awfully round. So we took out our microscope, and we took this picture. And I will remember for the rest of my life how I felt, where I was standing, and the unrepeatable words that I said when I first saw this picture. The surface of Mars at this landing site is littered with an uncountable number of little round things. And they're 4, 5, 6 millimeters in diameter, and they are absolutely everywhere. We had no clue what we were dealing with. We drove over to the outcrop, and what we realized was that the little round things are embedded in the bedrock like blueberries in a muffin. The muffin is soft, and the muffin erodes away. The blueberries are hard, and the blueberries fall out. And they're everywhere. We were very puzzled. Now, we suspected that these things were probably made of hematite, and we wanted to measure the composition. This is a picture taken with our microscope, shows one of the blueberries in the layered muffin rock. The problem was that our instrument looked at a pretty large area, something that was maybe 5 centimeters or so across, and so in order to measure the composition, we couldn't just isolate one of these little things, one of these little blueberries. We needed instead a gathering of blueberries. We found one. We found a place where there was a little bowl-shaped depression in the rock that a bunch of the blueberries had rolled down into. We named it the berry bowl. And we stuffed our spectrometer into the berry bowl, and what we found that indeed these little round blueberries are made of hematite. What we came to realize is that the blueberries are what geologists call concretions. Concretions form on Earth typically in sedimentary rocks that are saturated with liquid water. There's some mineral like hematite that's dissolved in the water. It wants to precipitate out because it's supersaturated. It finds a little nucleation point and it starts to precipitate. And what it does is it grows and it grows and it grows, like the way an oyster builds a pearl. And it builds this little hard spherical nodule in the rock. So these hematite blueberries are telling us again that this was a place that was once soaked with liquid water. It's a place that would have been habitable. After leaving the little crater that we landed in, one of the first things we went to was our heat shield. If you recall, the heat shield is the thing that protects the vehicle as it's coming down through the Martian atmosphere. You can see it at the top. That's what it looked like last time I saw it at Cape Canaveral in Florida. Here it is at the bottom, busted into pieces on the surface of Mars. We just drop it when we're done with it. It falls, hits the ground, going really fast. You can see the crater that it made when it hit, and there it is broken into pieces on the surface of Mars. Now, we went to the heat shield not to learn about Mars, but to learn about heat shields. Okay, for decades, engineers have been given the task of trying to design a heat shield that will work properly in the very poorly known Martian atmosphere. Ours was the first mission where we were able to drive up to the heat shield. It had broken, so it had an exposed cross-section. We could take our microscope and take an image through the cross-section of the heat shield and give it to the engineer who had built it so that they could assess how well it had performed. So it's a very nice engineering investigation. Now, we're scientists, so at the same time we're doing this engineering investigation, we're looking around for rocks. Okay, and it turns out 2 meters away from the heat shield, right next to it, there was a rock. We named it heat shield rock. It turns out the heat shield rock is not made of conventional rock at all. This thing is made of a nickel-iron alloy. It's a meteorite. It's a great big metal meteorite that was sitting there right next to the heat shield, pure dumb luck. I told the team we shouldn't stay here. It's obviously a place where big metal objects fall from the sky. We drove away from the heat shield, and we began a long, long, arduous drive to the south. As we drove farther and further south, our circumstances changed, and we found ourselves driving into a bit of a dune field, little sand dunes. And we made tracks through them, and you could see we were doing fine. We drive over one, and drive over the next, and drive over the next, and we were doing really, really well. And then one day, and I still don't completely understand this, but one day we hit one of these dunes that was just a little bit different somehow from all the others. And we did 50 meters worth of wheel turns thinking we were driving across the terrain when in fact we were just digging ourselves deeper and deeper and deeper into the sand. We came in the next morning, and all 6 wheels were buried over the hubcaps. This was a very bad day. Now, when something like this happens on Mars, the first rule is don't do anything stupid that's going to make the problem worse. Stop what you're doing. The sun is shining, we've got power, the rover's not going anywhere, we've got time to figure this out. Now, when we built the rovers, we actually built 4 of them. We built Spirit and Opportunity, which we sent to Mars. And then we have 2 more back on Earth that we can use to simulate predicaments that we've gotten ourselves into and then try to figure out how to get out of those predicaments. In order to simulate this particular predicament, what we needed was a very large quantity of fake Martian soil. If you were ever called upon to create fake Martian soil, here is the recipe that I recommend that you use. It is equal parts play sand, the stuff that's used in kids' sandboxes, clay, and diatomaceous earth, the stuff that's used in swimming pool filters. Once we figured out this recipe, engineers in pickup trucks fanned out across the LA basin and bought up literally tons of these 3 ingredients. People were getting algae in their swimming pools all summer long because of us. And we brought this stuff back to JPL and we mixed it up together. Horrible work. You see people wearing face masks. And we made dunes and drifts and pits, and we drove the rover into it, got it stuck, just like it was on Mars. And then we spent 2.5 weeks rehearsing, trying to find the optimal technique for extracting a robot from a sand dune on another planet. A lot of things you can do. Okay, you can run the wheels at different velocities. You can steer the wheels back and forth to open up the holes that they're in. You can rock the vehicle. Okay, we tried all those things and many, many more. And after 2.5 weeks, we found the optimal technique. The optimal technique, it turns out, was to put it in reverse and gun it. There's no place you go to look this stuff up, folks, okay? So here we are, gunning it on Mars. Because that's the left front wheel. This is the left rear wheel. We were really stuck. We did 192 meters worth of wheel turns to get the rover to move 1 meter. But one marvelous Saturday morning, after 6 weeks stuck in a feature that we later named Purgatory Dune, the rover popped out, and we have been treating those dunes with much greater respect ever since. So let's see. This shows where we've been working. You can see Eagle Crater down there where we landed. Notice the 1 kilometer scale bar. That's how far the rover was designed to drive over its lifetime. Eagle Crater, Endurance Crater, the heat shield was close to Vostok. Purgatory Dune was about here. Our goal was Victoria Crater. Look at that thing. 800 meters in diameter, 120 meters deep, an absolutely spectacular feature. You will notice that the names of these craters all come from famous ships of exploration. So Eagle, of course, was the Apollo 11 lunar module. Endurance was Ernest Shackleton's ship. The Victoria was one of Ferdinand Magellan's ships. Magellan left Spain with 5 ships. Victoria was one of them, and 260 men on a voyage of circumnavigation. Magellan himself was killed in the Philippines. After 3 years at sea, the one surviving ship, the Victoria, sailed by 18 surviving sailors from the original 260, finally limped back to Spain. So we chose that name for this crater as an apt analogy, thinking that if we ever made it there with our poor beat-up little rover, it would be driven by 18 surviving graduate students. But in fact, I'm very proud to say that we made it. And in a wonderful coincidence, at almost the exact moment that we pulled up to the rim of Victoria Crater, a new NASA orbiter called the Mars Reconnaissance Orbiter pulled into orbit around Mars, turned on its camera, and one of the first pictures that it took was this picture of Victoria Crater. I'm going to blow up just that part. There it is. If you look close, there's the Opportunity rover. In fact, if you look really close, you can see the shadow of the camera mast being cast on the Martian surface. It was really, really, really nice to see our rover again. We spent 2 years exploring Victoria Crater, much of it driving along the rim of the crater. You can look at the wheel tracks. You can see the wheel tracks that we made along the rim. The rover drivers told me when that was all done it was going to spell out, "Hi, Steve." And I'm not seeing it. But seriously, to me, those wheel tracks represent one of the finest accomplishments in the history of planetary robotics. We're driving along the top of a 6-meter, 8-meter tall cliff. And you've got a bunch of engineers whose job is to keep the vehicle safe above all else. And you got a bunch of scientists saying, "Go closer, go closer, go closer." And they took us right to the rim over and over again. We got spectacular images. Here's one. This is a place called Cape St. Mary. I'll blow up just a part of it. There it is. Look at the layering in that rock. Spectacular layering. This is what geologists call cross-bedding. What you're seeing here is the remains of ancient sand dunes on Mars. Okay, you could show this rock to a terrestrial geologist, and if you told them that was the Navajo sandstone in Utah, they would believe you. It's just a textbook example. I don't know if you've been to many talks by geologists. Whenever geologists take a picture of an outcrop, they take the rock hammer and they put it into the picture for scale. So there's my digital rock hammer. Believe me, I wish it were my real one. I got 5 minutes of stuff left. Endurance Crater, there's Victoria Crater. We set as our next goal Endeavour Crater. Endeavour Crater is huge, 22 kilometers in diameter, spectacular hole in the ground, and the rim is made of materials older than anything we have ever seen on Mars. It took us 3 years of driving to get to Endeavour Crater, but 3 years ago we reached it. This is a picture that we took just before we drove up to the rim of Endeavour. Spectacular, spectacular feature. We have found wonderful things at Endeavour Crater. This is just one example. This is a vein of a mineral. This thing is about as wide as your thumb. It's about as long as your forearm. This is pure gypsum. Gypsum is calcium sulfate salt. This stuff precipitates from liquid water. So there were fractures in the ground here that water just gushed through. Again, this is a place that was a habitable environment. This is a place where we spent a lot of time. This is a false color image. We calculated it out. In order to get to this valley where we spent about a year exploring, we had to drive exactly 26.2 miles, so we named this Marathon Valley. As we speak, Opportunity is exploring here. If you look, cutting across the middle of this image, okay, is a gully that we believe was carved billions of years ago by flowing liquid water. These gullies have been seen from orbit for decades. They've never been explored in person. We saw this gully years ago. It has been a goal that we've been trying to get to for 6, 7 years. We are there now. We are inside it. We have named it Perseverance Valley because it took so long to get there. This picture came down today. This is viewed using some of our three-dimensional modeling tools. Here, this is an image from this afternoon. What you're seeing, look at this kind of scoured appearance to the rocks here. We don't know how that scouring took place. It could have been sandblasting by wind, or this could be the signature of flowing water billions of years ago on Mars. We're working it out. I don't have an answer. If I come back some future talk here, I will tell you what the answer was, but we're still working this out. This is science that's happening right now. I wrote a book about the project called Roving Mars, and in an appendix of that book, I made an attempt to list the names of everybody who has worked on the project. There are more than 4,000 names on that list. I'm just one of them. This is some of the team. This is down at Cape Canaveral. This is the night that we took the Opportunity spacecraft, which you can see there, out to the launch pad. For every one of us who has had the remarkable experience of being part of this mission, it has been, in the literal sense of the phrase, the adventure of a lifetime. And I want to thank you very much for inviting me here to tell you about it. Thanks. Lights up. There we go. Thanks a lot.
This is celebration in science. Thank you, Dr. Squyres. So we have got 10 minutes for question and answer. There are 4 such portable microphones, one in each of these particular aisles here, and one in each of the upstairs aisles. So we are going to take questions from number 20, 21, 22, 23. And we'll just try to get as many questions as we can. So here is the first question from number 20.
Question, somewhere. Yep, there you go.
In the picture that with the coin next to it, what was that again?
The picture with...
The coin.
Wow. That was, I think there was a coin for scale? Yeah, okay. Those were the cameras. So on the front end of the rover and the back end of the rover, there's some cameras. And they have pretty big lenses. And the reason for the coin was just to show you how big the cameras are. But the camera lenses themselves are about that big. They're bigger than your eyes. They're about like this.
Okay, question there.
Hey.
How much Earth time is in a Martian day?
Oh, that's a great question. How much Earth time is a Martian day? A Martian day is 24 hours and 39 minutes long. And the reason that's important and interesting is that for the first 4 months after these vehicles landed on Mars, all of us on the science team and the engineering team lived on Martian time. We lived a day that was 24 hours and 39 minutes long. Now, you might think that it's cool to be able to sleep in an extra 39 minutes every day. It is not, because here's what happens. If the daily planning meeting is at noon today, tomorrow it's got to be at 1:39, right? 39 minutes later. The next day it's going to be at 1:18. And you go forward, and 2.5 weeks later, yeah, you're getting up in the middle of the night. So we're going around the clock. We had blackout curtains on the windows. We had watches that ran on Mars time, alarm clocks that ran on Mars time. We had food service. We had housekeeping service on Mars time. I had to take my team. Everybody's living on Mars time, but I had to split the team in half. So I got everybody living on Mars time, but in 2 different Martian time zones for the 2 rovers. Wait, it gets worse. If you're on one rover and you want to switch to the other one, you get Martian jet lag. The rovers are on opposite sides of the planet. Changing rovers was like getting on a plane and going to India. So Mars time was a pretty screwed up way to live. We did that for about 4 months and then we quit. Great question.
Cindy.
How long have we had rovers on Mars?
How long have we had rovers on Mars? We have had rovers on Mars. Okay, let me see a show of hands here. Who in the audience was born before January of 2004? So who is less than 14 years old? That's awesome. That's awesome. We've had rovers on Mars for 14 years, and everybody with your hands up, there's been a rover on Mars your entire life. I just think that's cool.
Next question.
Up here, yeah. I don't know, we need a microphone. You got a microphone?
Okay.
Yeah, go.
Has the rover experienced any storms or?
Has the rover experienced storms? Yes. So these are solar-powered rovers. They depend on sunlight for their very survival. There's dust in the Martian atmosphere, and every now and then Mars has dust storms. Sometimes those are little dust storms, little regional or local things, but every now and then, and it's only happened to us once, I believe it was in 2007, a storm blows up and becomes a global dust storm. Okay, and the entire planet is blanketed by dust. Now, has anybody seen the movie The Martian? Okay, great movie, but that storm at the beginning, no. Mars does not do that, okay? That was the only thing that was really wrong with that movie. But when you think Martian dust, don't think gravel, Don't think sand, okay? It's not going to knock Matt Damon down, okay? Think cigarette smoke. This stuff is incredibly fine. But you loft it into the air and it blankets the planet. And there was a dust storm in 2007 where we would take our cameras and look up in the sky at where we knew the sun was and we could not see the sun. That's a scary, scary situation for a Mars rover. It was very bad for Spirit, and it almost killed Opportunity. I think if it had gone for another 2 or 3 days, Opportunity would not have made it. So yeah, we've had some storms and they were bad.
Lonnie?
How often do lunar eclipses occur?
I'm sorry, say that again, please.
How often do lunar eclipses occur?
How often do eclipses occur? Oh man, I don't know. What is the interval between solar eclipses on Mars? You know, it's measured in months, but it's irregular. It's not like they occur at regular intervals. They will occur, the timing has to be right. I'm kind of waving my hands, but honestly, I don't know. You know, I give talks like this all the time, and it's very rare for somebody to come up with a question that stumps me, and you did it. Well done.
We have the answer right here.
Cindy? Okay, go ahead.
Are you guys able to fix the tires on Mars?
Are we able to fix tires on Mars? Well, okay, I know what you're referring to. There have been 3 big rovers that have been sent to Mars. There's Spirit, Opportunity, and then there's a rover called Curiosity. Curiosity is the one that has problems with the wheels. The Curiosity wheels are much bigger than the wheels of Spirit and Opportunity, so they were made a little thinner, a little less strong. And what we found with the Curiosity wheels is that they've gotten holes poked into them by sharp rocks. There's no way of repairing that. It's just damage that accumulates. It's nowhere near being bad enough that it threatens the mobility of the vehicle, but yeah, we're poking holes in those wheels. There's no way to repair them. Opportunity and Spirit have much sturdier wheels, and we've had no problems with the wheels on those. Who's next? Yeah.
Is Opportunity or Spirit still sending you pictures?
That picture came down from Opportunity this afternoon. Ask me again tomorrow. Could die overnight. I don't know. It's been 14 years. But yes, Opportunity is still going strong. Yeah.
Where do you want Opportunity to go?
Ooh, that's a great question. Right now, what I want to do is I want to continue exploring Perseverance Valley. So Perseverance Valley is this long, snaky kind of valley, okay, and it's pretty steep. It's about 15-degree slope, so it's about like this steep. And what I want to do is I want to drive all the way down it, the whole length of it, all the way down to the bottom, because the stuff at the bottom might be different from the stuff at the top. Once we do that, we'll be down inside that great big crater. So now we got to get out. We can't climb back up. It's too steep and too dangerous. But we know from looking at pictures that if we drive about 3 kilometers to the south, there's an escape route out of the crater. We're going to drive down the south, we're going to escape out of the crater, and then we're going to decide where to go next. There's another crater. It's beautiful. It's spectacular. It's called Iazu. It's about 17 kilometers to the south. It makes me tired just thinking about it. But if we manage to escape from this crater, we'll probably go to that one next. Great question.
Is there a mission anytime soon to send a human to Mars, so it's like a little bit easier to collect evidence?
Humans to Mars. You know, there's a lot of talk about it. There's a lot of excitement about the subject. Can't happen soon enough for me. You know, I'm getting lots of exercise. I'm eating healthy foods. I'm 61 years old. I'm not going to go, but I want to live to see it. If you're about maybe 15 years old right now, you're just the right age to go to Mars, or younger. I think it's probably going to happen easily in the next 30 years, maybe in the next 20. Like I said, it can't happen soon enough for me, but there are no near-term plans to make it happen. If you read about plans to send people to Mars, those are not plans, those are wishes. The difference between a plan and a wish is that a plan has money behind it.
Anna.
Are you planning on sending any more rovers soon?
Yes, so there's a mission that's being planned right now. I'm not personally involved in it because I chose not to be. It's called Mars 2020, and as you might imagine, in 2020 it's going to send another rover to Mars. That rover looks a lot like the Curiosity rover, but it has a different job. Its job is to collect some samples that will then subsequently on another mission be brought back to Earth for analysis. Very challenging task. I've been working on Mars rovers for 30 years, and I chose not to try to get involved in the Mars 2020 mission because frankly I think it's time for some younger people to step in and do the job now. So I'm backing away from that. But yeah, Mars 2020 is going to be a really exciting mission, and that's going to launch in about 3 years.
Cindy.
If you sent another rover to Mars, what would you add to it?
If I sent another rover to Mars, what would I add to it? Good question. I mean, things that I would like to have on Spirit and Opportunity, we have on Curiosity. So, for example, I would like to have a nuclear power source so I don't have to rely on wind gusts to clean off solar arrays. Curiosity has that. I would like to have a really sensitive instrument for analyzing organic molecules. Okay, Curiosity has that. Most of all, I'd like the capability to bring samples back from Earth, and the Mars 2020 rover has that. So all the things that we'd like, they're eventually going to happen, but it takes a long time. You got to take kind of a long view in this business.
It is 8 o'clock, and we will be formally adjourning this particular session. Two things. Number one, that within 10 minutes in the cafeteria downstairs, we are going to have another session. There is a Young Scientist Roundtable Part 2. There will be plenty of time again there, 30 minutes for question and answers. So if you can come there, that is great. Second part, that most of you probably know that the speakers that Young Scientist Roundtable gets are the volunteers. They believe in our mission of promoting science at a young age. Here is one example. Dr. Squyres has come here from Ithaca, New York. So he's a volunteer, he believes in our cause, and an appreciation of his effort to come and re-educate us about the science of Mars. Here is a token of appreciation from Young Scientist Roundtable.
Oh, excellent. Now I have a matching set. Thank you.
So on November 14, we will have a chemistry-related topic, chemistry of sugar. That is a speaker coming from Iowa. And then on December 4, we have Dr. Michael Osterholm, who will be talking on the subject of infectious diseases. Okay, see you down there.